The Part 2, Chapter 5 continues our discussion over irrigation systems. And we'll start off by talking about something called fertigation. Fertigation is made up of two words that we're familiar with, fertilize and irrigation, and it's exactly what it sounds like. We're basically incorporating the nutrients for the plants right into the irrigation water. So water-soluble fertilizers are mixed right into the water using a variety of equipment and methods, and we're going to kind of take a look at some of that equipment in the next few slides. The reason liquid fertilizers are popular and fertigation in general is popular is because it tends to be more controllable than granulated fertilizers that would sort of be slow released into the soil. And liquid fertilizers allow growers to maintain a more precise and flexible control of the application, timing, and the quantities than the slow release mixed into the growing media. There's a wide range of equipment from the basic hose siphoning units to more sophisticated computer-controlled mixing stations, which is what we're looking at here. And the majority of these systems are designed to be run automatically based on sensors and then control valves and pipes and pumps and all the other stuff we would expect in a normal irrigation system, but with the addition of injectors that pump the nutrients into the irrigation water. So the design of the system really needs to be done by somebody with some experience, preferably a professional, and possibly even the company that you would purchase the equipment from can help with that design. But the design of the complete system would include sizing of the system. That's really important, and it would be based on the size of the growing area and the amount of fertilization and irrigation that would be required. The positioning of the pumps, where those are going to go in the system. There's going to be valves, piping, sensors, of course, so that it knows, how and when to add the fertilizer to the liquid. The computer control system that runs it all, and then of course there's going to be a number of storage tanks. Typically the design is going to start at the plant and work backwards. So in other words, the crop itself is going to drive what everything else sort of ends up being. So the designer would need to know the type of crop that's being serviced, the amount or quantity, the frequency of the feed that the plants you're working with need, and all of that is going to drive the type of the irrigation system that's going to be installed, how much water pressure is needed and how much volume is needed, which of course relates to pipe sizes and pumps and things like that. And the particular plant needs are going to drive what chemicals will be used. So the book does point out that it's really important to work with a professional who's familiar with this stuff. There's a lot of DIY people in the controlled environment agriculture industry, and all of us need to understand our limitations, especially when we're going to make a large investment like this. It's usually best to pay a little bit more and get some professional help. Number 4, perform routine checks, is referencing the importance of making sure that an automated system like this is functioning properly. The last thing you want to do is wait until you see a problem in the crops, because then it's too late. And by a problem in the crops, it might mean that the plants are receiving too much or not enough nutrients. And by the time it starts showing up in the color of the plant or the health of the plant, it's possible that they won't be recoverable. So testing that equipment regularly, manually, various methods, is an important step as well. This is a basic layout for a fertigation system, and it goes along with a little bit of terminology. The day tank is a holding tank for just regular water. It stores about 1 day's worth of irrigation water that's needed. And although you might think that this is a wasted step, having that irrigation water in a tank in your facility is actually a really good idea, because you never know if the water is going to go down. Plants don't do well if they don't get their daily watering. And so having that day's worth stored up is a good idea. It also has the advantage of being able to bring that water to room temperature so that it's not too warm or too cold based on the outside environment that it came from. The term salts is actually referring to the nutrients that are going to be used in the stock solution. The stock solution, of course, is the mix of nutrients to be added to the irrigation water. The dilute tank is another storage tank. This one is a tank that holds the pre-mixed water and nutrients ready to be delivered to the plants. And then the feed line is, of course, the pipes that carry the nutrient water to the plants. There are various types of distribution systems that can be chosen for any given operation. We'll just kind of go through each one. There's one called the home run piping system. This is where individual pipes run from a source to each zone. So we could sort of think about we'd sort of break the greenhouse up into different zones based on their various watering and nutrient needs. This one is a little bit expensive because it requires a pipe for each zone, a separate pipe for each zone. So you could sort of think of that as just multiple pipes running through the greenhouse. Each one could potentially carry a different solution based on the requirements of an individual zone. There's also one called a single common main, and that's one where a single pipe serves all irrigation zones, and then valves right at the zone would open and close based on the nutrient needs. This is the most common arrangement. In this case, only one recipe can be delivered, unlike the home run system where each zone can have a different recipe. The multiple common mains has one main pipe delivering nutrients to plants, but is fed by multiple nutrient sources, so the recipe can be altered and delivered to all the plants. And then the common main system, either one of the common main systems, can also have a supplement that is delivered at the zone itself. So the recipe can be the same for all the zones until the water gets to the zone, and then a specialized nutrient can be added right at the zone so that each zone can be different in that way. So kind of just a lot of different ways that we can deliver the nutrients to plants. Some of them are more flexible than others. Some of them are less expensive than others. Also in the equipment category of fertigation systems are the injectors. And the injectors are basically just valves that open and close. Some of these injectors are very sophisticated, other ones are fairly simple. And generally speaking, the more sophisticated, the more expense, but also there are going to be various benefits that come with that sophistication. It's important for a grower to understand the capabilities of all of these different types of equipment and to choose only as much sophistication or cost as what's needed for their particular crop. Fertigation equipment also requires something to control the injectors. So there are various types of controls that we can have for the injectors. The first one, of course, is the fixed control. This just uses a small manual adjustment knob, and you can kind of just think of that as a ball valve, and you can adjust how much nutrients are going in just by turning the valve with your hand. Obviously, that's going to be a lot less accurate than some of these other ones that are available. The set point, EC, and pH control ones, they use a combination of flow meters and sensors to test the EC and pH levels in the water, and then that'll automatically adjust the flow of the nutrients into the water based on the need at any given moment. The integrated volumetric recipe control also uses EC and pH sensors, plus it has multiple stock solutions that it can draw from to create varying recipes. So as we go down this list, we're getting more sophisticated and also more expensive. And then finally, the separate salts output control. That's going to be basically the same thing as the previous one, the integrated one, but it also adds the ability to adjust the ratio of each individual stock solution based on the sensors, what the sensors are telling it about the water that's coming into the system. So if the pH levels of the incoming water are a little higher, it can make an adjustment to bring those down. And if it's a little lower, it can make an adjustment to bring it up to whatever value is desired. As with any investment, it's a good idea to have a sense of how long these things live and how much they cost initially and over time. So the sensors need to be checked regularly for fouling and how accurate they are. So manual tests on the water that the system is putting out should be done regularly, just to make sure that the sensors are sending the right signals to the injectors and that everything is working the way that it's supposed to. So the EC sensors, they often last many years, but they do require occasional cleaning. And that's really true with anything that's going to be exposed to water regularly, right? Because water, it does have corrosive elements to it. It does cause oxidation, but also it's going to have minerals in it, and those are going to build up on things. And when minerals build up on a sensor, obviously that's going to reduce the sensitivity and probably throw off its accuracy. The pH sensors also should be cleaned and calibrated regularly, but these typically are only going to last maybe 1 year, and so the book definitely recommends replacing pH sensors every year, and that should just be built right into the budget. The injector costs for a simple system may be kind of around $700 on the low end, and all the way up to maybe $30,000 to $50,000 on the high end dollars. So again, it's important to weigh the costs of the sophistication that you're willing to buy against what the output is going to be, how much you're going to make on the crops, and make sure that you're not pricing yourself out of the market. The design of the fertigation room is important to think about, where everything's going to be laid out. And again, someone who has done this a lot is usually the best person to consult on laying something like this out. It'd be really easy to sort of have a plan you think works really well, but if you don't have a lot of trial and error experience to lean on, you're probably going to make a lot of mistakes. So the fertigation room is actually called the crop kitchen. That's sort of a slang term, I imagine. But this is an area that's set aside for mixing all of this fertilizer with the water, and it's going to house all of the equipment, probably some of the controls. There may be chemical storage in there and things like that. So this room really needs to be lockable, and it needs to be ventilated and away from people, ideally. We wouldn't want to use the same space for the crop kitchen as we would, say, for like a work area for workers. We don't really want people to hang out in here. So we really don't want it to be a huge area, and it should be isolated, but also it should be separate from where people work regularly. Also, we don't want this space exposed to natural sunlight, because this could sort of promote algae growth, and sunlight happens to be hard on some types of plastics like PVC, and it's going to break down a little bit quicker. So some dark area without windows is ideal. We're also going to want to make sure that there's a large sink or series of sinks with hot water. An eye wash station would be really important anytime you have a lot of chemicals, being able to get those chemicals off of you. I would say, the book doesn't mention it, but I would say also, in addition to the eye wash station, a shower, right? If you get some chemicals on your face or in your hair or something like that, we want to be able to get that off quickly, depending on what it is. And then, of course, there really should be a floor drain inside of a curbed or sloped floor area to catch and clean up chemicals should a spill or a leak happen. And then this also should be led to an isolated sump, not directly into the city sewer or the storm drain, because we don't want those chemicals released out into the environment. So kind of a lot to think about with the design of the crop kitchen. Some other design considerations, pH correction. So most water, as mentioned previously, are going to run a little high in pH. So reducing that by adding acid is usually needed. If you end up with low pH, you may have to add base, but one way or the other, it's probably going to have to be adjusted. And then there should be some stock tanks. You see some examples of that in this image here. It's advisable to size those stock tanks to store several days of the stock solution. And all of that stock solution, the fertilizer needs to be mixed oftentimes with hot water between 140 and 160 degrees to dissolve the soluble fertilizers. And then the outlets, as you can see down there at the bottom where it comes out into those hoses, should be 2 to 3 inches from the bottom, just because we don't want to be pulling solids into the injection equipment. That's going to clog it up. So we let those solids settle to the bottom, and we have that outlet just a little bit above the bottom of the tank. There needs to also be a filter of some kind, and so if solids do get into the system, it doesn't just get sucked right into the injectors. It's going to go through a filter first and just make sure that any large particles are going to get caught in that filter. And then the book points out filters downstream of the injectors is also a good idea to remove any sediment. In terms of water hammer, what we want to avoid is when valves open suddenly or close suddenly, we don't want that to vibrate the pipes too much. And there are devices that are common devices that are in most plumbing systems in houses and buildings that prevent water hammer. And it basically is just like a shock absorber that functions to ease that sudden transition between flowing water and not flowing water. We don't want it to bang shut, basically. So you have something that sort of receives that pressure and softens the blow when it stops suddenly. Water hammer can usually be prevented by just sizing pipes correctly and then selecting the appropriate valves that maybe open and close a little bit slower. But water hammer arresters can be added if needed. And then finally, backflow prevention. This is talking about if the municipal water supply, the pressure drops for some reason, if the municipal water supply's pressure, it loses pressure, we don't want that water in our facility to flow back into the water supply for obvious reasons. We don't want fertilizer in our potable drinking water. And so it's required, most municipalities are going to require backflow prevention so that nothing comes back through the system if you lose pressure. These next few slides talk a little bit about water recycling and sanitation. We need to keep in mind that water is a finite resource, and historically in the U.S., it's been pretty plentiful. Not everywhere, but certainly in most parts of the U.S., we've had plenty of water, but largely that's because we've had smaller populations. And as the population grows, and as the climate changes, frankly, we're getting less water available. The aquifers underground are getting depleted at a pretty alarming pace. The water above ground, and we're looking at the Colorado River here at Hoover Dam, as you can see, we're sort of at record lows in this area. And this doesn't happen all at once. We'll probably have fluctuations in the amount of water that we have and the amount of rainfall that we have. But over time, the trend is going down, right? The increase in our usage and the decrease in the supply is a bad combination. So thinking about recycling water rather than just burning through it without a thought about tomorrow is becoming increasingly important, and it also happens to save cost. The other issue, though, is that at the same time, water pollution is on the rise, and our industrial systems involving manufacturing, mining, farming, all of these things contribute to water pollution, perhaps in a small way, each of them, but you combine it all, and it can become a real problem. So there's increasing regulation on the use of water, but also the disposal of water, and even the cost of treated water is going up. So for these and other reasons, water recycling is an increasingly attractive option for many growers. The first thing to do before designing and purchasing a system is to consider how water can be reduced first. So we want to identify and eliminate any kind of overwatering. So that would include training staff in the proper methods for hand watering, reducing the overspray by optimizing the spray patterns that are being used, especially on automated equipment, Make sure that the equipment itself is maintained and that leaks are fixed regularly rather than just allowing them to drizzle all over the floor and waste that water. And then optimizing the automated equipment by using sensors instead of just timers. It's really easy to over or underwater by guessing the wrong amount of time, and sensors do a good job of detecting how much water is in the soil, how moist the soil is, and then shutting the system off when it reaches the right level. So the recycling system can be made smaller and less expensive if we can first get out there and figure out how we can use as little water as possible. The less water we use, the less we're going to have to think about recycling. The next thing we got to do is find the money, find the funds for a system like this. As much as 50% of the cost of water conservation systems could be paid for by tax incentives, grants, or interest-free loans. That's a big chunk. And so going out and looking at what's available, doing a little bit of research ahead of time, can save a whole lot of money. Also, many sustainability incentives exist under the recently passed U.S. Inflation Reduction Act, which it's anybody's guess how long that incentive will last, but for the time being, folks are aware of that. Folks know that that money is available, that resource is available, and if you're in the business that qualifies, why not cash in on it? So some people might ask the question, why recycle? I think we've already sort of covered some of that, but there are basically three reasons. Number one, we have to, right, in some cases. So regulation is going to drive some of that recycling necessity. You can expect to increase what we're going to see in terms of regulation well into the future. The trend is increasing regulation on water usage, both in terms of discharge and incoming water use. And so that trend is not going to change because the problems are not going to go away. Goodwill is another reason to recycle, and goodwill, it might be an altruistic thing where we just feel better about ourselves, about using less resources. We feel like our operation is sustainable. But the other side of goodwill, even the non-altruistic side of it, is that we can tell people that we do these things, right? And sometimes customers respond positively to that, and it might actually contribute to increased sales. And then the third reason, and perhaps the most motivating, is the financial benefits. Reduced water means reduced fertilizer costs, especially if you're running a fertigation system. So if we're not wasting all of that runoff, we're able to bring it back around and run it through the system again and save money. So some alternatives to recycling that we see. One, the discharge water must be permitted, usually must be permitted and or treated prior to putting it back into the environment. So as you might imagine, that can be costly because treating water and getting it back to its natural state, that requires equipment, additional equipment, right? Additional chemicals, additional this, that. And so that's going to add cost. In some cases, though, that cost of bringing that water back to a natural state is less than recycling it. So some people would choose to do that. Also, some facilities are so efficient in the equipment that they use, they may not have enough discharge to really justify trying to recycle that water. So it's less expensive for those particular people to just fix the water that they waste and then put it back into the environment. And some jurisdictions don't regulate discharge yet. However, that's getting increasingly rare. So what water can or should be recycled? Basically all of it that can be captured, right? So you got your leachate runoff, which is water that has passed through the plant soil. You have overspray or overdrain, excess irrigation that doesn't make it to the plant container. It just maybe ends up on the floor or something. Dump water, water that has accumulated excessive levels of certain salts or particulates. So the mix is just, it's not sustainable anymore. We can't use it on our plants. It's too rich. So that might be something that we would need to recycle in some way. Condensate, water generated by dehumidification or air conditioning units. And of course, rainwater. I mean, we wouldn't really think of recycling rainwater, but we can certainly capture it and bring it into our system. So rather than letting it run off, and that is regulated in some areas. It's not okay anywhere in the United States to just collect rainwater. Some places don't allow you to do that. They want it to run into the systems and recharge aquifers and so forth. And then finally, filter backwash. Filter backwash is just water generated by cleaning out the filter equipment, which does have to happen every once in a while. So the final slide in this presentation discusses how to recycle water. And that, of course, is a multi-pronged approach, and no two systems are going to be exactly the same. However, there are some common things that each system is probably going to have. Number one, probably the most important, is you got to capture that water. So there has to be a method by which you can collect that water that's being wasted that we were talking about on the previous slide. And each system should be evaluated individually, but may include things like troughs or gutters, drains, pumps, tanks, hoses, and the like. These things that we already use for transporting other liquids around. Storage. Obviously, we're going to have to put this water someplace, so we're going to have various tanks of different types. For example, one to store dirty water and one to hold the treated clean water that we ultimately are going to cycle back into our systems. Treatment considers the effects on plants first, and then treating for discharge and treating for reuse. Those are clearly different processes, and so we have to think about what we're going to do to the water, whether it's going to come back into our system, which is one way of treating it, or we're going to discharge it out into the environment, which is a totally different way of treating it. Some of that treatment might involve killing pathogens, right? So that water might be growing nasty things, but killing pathogens is similar to killing plants. So we're going to be using acid and chlorine. So care needs to be taken on that, not to put too much in if we're going to be reusing that water to irrigate our plants. Biofilm is another thing. Controlling biofilm. Biofilm exists on every surface exposed to water for more than a few minutes, and it's often invisible to the naked eye. So we need to think about how we're going to control that. Filtration is good for the removal of particulate, that is particles, but it can't remove all pathogens. Some are just too small and will slip through the filter. So in that case, chemical treatments would be necessary. And then finally, the reuse options. And most often, water that has been recycled or treated in some way is going to be mixed back in with fresh water and then run through the fertigation equipment to top off the nutrients. So for example, if your recycled water already has maybe too much nutrients, we're going to water it down with just some regular fresh water, and then run it through our sensors again, and the fertigation equipment will top it off to the desired level of nutrients. So who knew there was so much involved in just collecting that water that we use for irrigation? There's all kinds of equipment that can be purchased for that. And in most cases, when you have a system where you're going to be increasing the efficiency of your operation, you're going to have a high initial cost. There's going to be an investment involved in that, and you might even have higher operating costs because of the time and the maintenance of that equipment. However, in most cases, when you increase efficiency, you bring costs down long term. So those short-term investment costs and mildly more expensive operating costs are often paid for by the efficiencies that you gain. Okay, that's going to do it for Chapter 5. Go ahead and take that quiz when you're ready. And if anything in this discussion doesn't make sense or you want to discuss it deeper, please don't hesitate to reach out.